This video is from section 6-1, Properties of the Normal Distribution, and it's going to look at the basic properties in the normal distribution, talk briefly about the standard normal, and quickly show you the formula for a z-score. Alright, so the definition there, a normal distribution is a continuous, symmetric, bell-shaped distribution of a variable. We're going to start to break that down. Number one, it's bell-shaped, and I'll see if I can hold this up here. The best thing to do is look at the picture at the bottom of the standard normal distribution table, table E in your book. And if you see there at the bottom of each page, there's a picture of the bell-shaped normal distribution. I apologize if you've got some reflection there, but you should be able to see that in your book. Or you can look in section 6-1 and find a picture. So it is roughly bell-shaped. I mean, any of you that have heard of the infamous bell curve, this is it. Now, property 2, the mean, the median, and the mode are all equal. They're all in the center, and there's only one mode. So if you look at that bell-shaped distribution, that mean, median, and mode all line up on that center line. Number 4 is an interesting one. The normal distribution is symmetrical about the mean. What that means is if you took that normal distribution graph and you folded it right along the mean, median, mode line, you'd have a perfect match. You'd have mirror images of each other, or in woodworking it'd be a book match. So the right and left half are mirror images of each other. Now, number 5. The graph is continuous. There are no gaps. We can calculate points along that line for any z value. There's not, it's not that you can only do it for 1 and 2 and 3. You can do it for 1.1786. Whatever number you come up with, we can calculate it for. Number 6, it never touches the x-axis. This graph keeps getting closer and closer and closer, but it never quite gets to the x-axis. Number 7, the total area underneath the curve is equal to 1, or 100%. This is fairly remarkable given number 6. You need calculus to prove that the area can be a finite number whenever it never quite gets to the x-axis, but for the purposes of this class, don't worry about the proof. Take that as the truth. Now, number 8 is an important set of relationships for this distribution. If you go from that center line, go 1 standard deviation to the left, so -1, and 1 standard deviation to the right, so you look at the center 2 standard deviations, that will contain 68% of the area. On the other hand, if we start at that middle line, we go 2 to the left and 2 to the right, so for a 4 standard deviation span, you'll get 95% of the area. And finally, if you go 3 standard deviations to the left, 3 standard deviations to the right, or 6 standard deviations, or 6 sigma, you'll get 99.7% of the values. So 99.7% of the values, as I mentioned, that was 6 sigma. Some of you may have heard of Lean Six Sigma and other quality programs like that, initiatives. That is loosely based off of, the title is loosely based off of this concept. All right, now, the standard normal is a special case of the normal distribution. In the standard normal, that mean, median, mode center line is at 0. And the standard deviation is exactly 1. All right, now, there are useful properties available for standard normal. In the next video, we're going to look at using it to solve some problems. But the good news is any normal distribution can be converted to standard normal through the use of z-scores. The formula for a z-score, z equals x minus mu divided by sigma. All right, so x is the target value you're looking at, mu is the mean, and sigma is the standard deviation. If you really stop and think about it, what the z-score is doing is it's actually calculating how many standard deviations away from the mean is my value x. So your z-score is negative if you're below the mean, it's positive if you're above the mean, and it finds out how close you are to the mean measuring by units of standard deviation. And that's essentially what happens with the standard normal.